Module 6, Changes in Matter and Chemical Reactions. The kinetic theory of matter. Are you sitting down right now? You may think that the seat you are on is still, but did you know that the molecules of that couch or chair are all moving around and doing it very quickly? The molecules and atoms all around you are constantly in motion, and this is the basis of the kinetic theory of matter. Now, it may not feel like your chair is moving at all. After all, you aren't moving around the room. But atoms and molecules are so small that when we look at things such as a couch or a chair, we are looking at trillions of atoms and molecules moving around in random directions. When material is in a solid phase, it doesn't look like it's doing anything because for each individual molecule that moves one direction, another molecule moves in another direction. So solid matter can't actually move anywhere because all of the molecules or atoms that make it up are moving in different directions. Now in the liquid phase, the molecules and atoms don't just vibrate, they can move around. If you were to put a drop of food coloring into a glass of water, you would notice that it eventually becomes completely distributed throughout the entire glass. That's because the food coloring molecules are bumped into by the water molecules, and they all move around randomly until they are spread out throughout the container. Molecules move in a certain direction until they hit another molecule or the glass molecules, where they will then bounce off in another direction until they collide with another molecule. It's kind of like the balls on a pool table when they are hit randomly and then bounce around moving in a straight direction until they hit another ball or the bumper on the side of the table. Then they careen off in a different direction. Now, atoms and molecules in the gas phase behave just like ones in the liquid phase, but the molecules just move around at a faster speed. They collide with other things less often because the atoms or molecules are farther apart from each other. Regardless of the phase, the atoms and molecules are all in some type of random motion. Now, because motion requires work and work requires energy, the molecules and atoms of a substance have to have energy to move around. It makes sense then that the higher the temperature of the material, the faster the molecules move. And the faster they move, the farther they get from each other. You see, when the temperature increases, the molecules or atoms of that substance absorb the energy. They move faster, going farther and farther away from each other, eventually changing phases. So that is why, for example, to change a substance from solid to liquid to gas, the temperature has to increase to make the atoms or molecules of that substance move faster and farther apart from each other. The temperature at which a substance changes from solid to liquid is called the melting point of that substance. And the temperature at which a substance changes from a liquid to a gas is called the boiling point. Conversely, when a substance is experiencing a decrease in temperature, the energy leaves its molecules or atoms and moves into the surroundings. That is because heat always moves from a hot body to a cool body. So as the molecules lose more and more energy, their motion decreases and they get closer to their neighbors. That results in a gas condensing to a liquid or a liquid freezing to a solid. To sum up, we can say that the kinetic theory of matter is this. Molecules and atoms are in constant motion. The higher the temperature, the greater their speed. Module 6, Changes in Matter and Chemical Reactions. Experiment 6.3. In this experiment, we're going to learn about how temperature affects the speed of molecules. So I have two mason jars here, and I have some room temperature water or cold water that I got from the tap, and then I have hot boiling water. And so I'm going to take I'll take the boiling water first and put it into one of the mason jars. You might be able to see some of the steam indicating that it's very hot. And then I'm going to put about the same amount of water that's cold into the other mason jar. This is a pretty simple lab, but it has a fun, cool effect. Now I have some food coloring. I'm going to put 1 drop of food coloring in each of the 2 bottles and take a look at what happens. Watch how the color distributes around the 2 bottles and compare the 2 to see which one distributes the coloring faster. This is the hot bottle and this is the cold one. Now what we should be seeing, and hopefully you're able to see there, the hot water container is distributing the
food coloring much more rapidly than the cold water. What's going on molecularly is when you heat up molecules, they have more energy in them and they move around. As soon as I put the drop of food coloring into both of the containers, the water molecules were bumping into those food coloring drops and making them move around, or the food coloring molecules, and making them move around, bumping into them, kind of like a pool table if you were bumping pool balls together, and knocking into each other. The hot water has a lot more energy, and so those molecules are moving faster, and therefore they're bumping into the food coloring molecules much more rapidly and dispersing them, which we can see spread them out much faster than the cold water did. So although this was a somewhat simple and quick experiment, it's a great visual to understand how temperature affects the speed of molecules.